Imagine a universe smaller than an atom, a realm so minuscule that it defies our comprehension. It is unimaginably hot and dense, a singularity of immense energy. Suddenly it explodes with a force beyond imagination. This is the Big Bang, the colossal event that set everything into motion. It marks the beginning of space and time, the very fabric of our reality. Everything we see around us, from galaxies to planets, originated from this single monumental event. In the first fraction of a second, the universe is a chaotic sea of energy, a turbulent and dynamic environment. The laws of physics as we know them do not yet apply, creating a realm of pure potential and possibility. The Big Bang is not an explosion in the traditional sense, but rather an expansion of space itself. It is the expansion of space itself, stretching and growing in all directions. Imagine a balloon with dots on it representing galaxies. As you inflate the balloon, the dots move farther apart, illustrating how galaxies move away from each other. Similarly, the Big Bang caused the fabric of space to expand, carrying galaxies along with it, spreading them across the cosmos. The energy released in the Big Bang drives this expansion, propelling the universe to grow ever larger. It also leads to the formation of matter and the fundamental forces of the universe, shaping everything we know today. Let's journey to a time so short after the Big Bang that it's almost impossible to comprehend. Planck time, a moment so brief it defies our understanding. This period lasts for a minuscule 10 to the power of negative 43 seconds, an almost inconceivably brief instant in the cosmic timeline. To put that in perspective, it's like comparing the blink of an eye to the entire age of the universe, a fleeting moment against an eternity. During Planck time, the universe is smaller than an atom and incredibly hot, a seething cauldron of energy and potential. We're talking temperatures exceeding 10 to the power of 32 degrees Kelvin, far beyond anything we can currently achieve or even imagine. At this extreme scale, the laws of physics as we know them break down, unable to cope with the intense conditions. Gravity, electromagnetism, and the weak and strong nuclear forces are unified into a single force, a state we can only theorize about. Einstein's theory of general relativity, which explains gravity, cannot fully describe this epoch, leaving gaps in our understanding. Quantum mechanics, the theory governing the subatomic world, also struggles to explain the conditions, adding to the mystery. Planck time represents a frontier in our understanding of the universe, a boundary where our current theories falter. It's a realm where the known laws of physics collapse into a singularity, challenging us to rethink the very foundations of science. After Planck time, the universe enters a phase known as the quantum foam era. This period, though still incredibly short, lasts longer than Planck time. Imagine a sea of energy constantly bubbling and churning. This is the quantum foam. Energy fluctuates wildly, creating tiny, short-lived universes. These baby universes pop in and out of existence like bubbles in a boiling pot. Within this chaotic environment, the universe is governed by the principles of quantum mechanics. The Heisenberg uncertainty principle reigns supreme. This principle states that we cannot know both the position and momentum of a particle with perfect accuracy. In the quantum foam, particles are constantly created and destroyed, borrowing energy from the vacuum of space itself. The universe is a chaotic, ever-changing sea of energy and particles, a far cry from the structured cosmos we observe today. From the chaotic quantum foam, the universe undergoes a period of rapid expansion known as inflation. In less than a fraction of a second, the universe increases in size by an unimaginable factor of 10 to the power of 26 or more. Think of a grain of sand suddenly expanding to the size of the observable universe. That's the scale of inflation. This dramatic expansion is thought to be driven by a mysterious force field called the inflaton field. As the inflaton field decays, it releases a tremendous amount of energy, causing space to expand faster than the speed of light. Inflation solves several cosmological puzzles. It explains why the universe appears so uniform on large scales, and why the cosmic microwave background radiation, the afterglow of the Big Bang, has such a specific temperature. Section 5. A quark soup, the building blocks of matter. As the universe cools after inflation, energy begins to condense into matter. The first particles to form are quarks and gluons. Quarks are the fundamental building blocks of protons and neutrons, which reside in the nucleus of an atom. Gluons are the force carriers that bind quarks together. Imagine, if you will, a hot, dense soup of quarks and gluons, constantly colliding and interacting. At these high energies, quarks are not confined within protons and neutrons. Instead, they roam freely in a state of matter known as quark-gluon plasma. This plasma is so dense and hot that it's impossible to observe individual quarks or gluons. As the universe continues to cool, the strong force, mediated by gluons, begins to bind quarks together. Section 6. Protons and neutrons, the heart of atoms. As the universe cools further, quarks combine to form protons and neutrons. Protons with a positive charge and neutrons with no charge are the building blocks of atomic nuclei. The ratio of protons to neutrons is critical. It determines the abundance of elements in the universe. At this stage, the universe is still too hot for atoms to form. Electrons, the negatively charged particles that orbit the nucleus, have too much energy to be captured by protons. The universe is a sea of protons, neutrons, electrons, and photons, constantly colliding and interacting. This period, known as Big Bang nucleosynthesis, lasts for about 3 minutes. During this time, the lightest elements, hydrogen and helium, are formed. Section 7. The Dark Ages, a universe in shadow. After Big Bang nucleosynthesis, the universe enters a period known as the Dark Ages. This era lasts for hundreds of millions of years. During this time, the universe is filled with a dense fog of neutral hydrogen gas. This fog is opaque to light. Photons, the particles of light, are constantly scattered by the hydrogen atoms. As a result, the universe is dark. No stars or galaxies have yet formed to illuminate the cosmos. The only light sources are the faint afterglow of the Big Bang, known as the cosmic microwave background radiation, and the weak radio waves emitted by neutral hydrogen. Section 8. Let there be light. The era of recombination. After hundreds of millions of years, the universe continues to cool. Finally, it reaches a temperature where electrons can combine with protons to form neutral hydrogen atoms. This process is called recombination. Recombination is a pivotal event in the history of the universe. Before recombination, the universe is opaque to light. After recombination, the universe becomes transparent. Photons are free to travel through the cosmos without being scattered by free electrons. The cosmic microwave background radiation, released at the moment of recombination, provides a snapshot of the universe at this early stage. Section 9. Cosmic Dawn. The first stars ignite. As the universe expands and cools, gravity begins to draw matter together. Small fluctuations in the density of matter, amplified by gravity, grow larger over time. These denser regions of gas and dust collapse under their own gravity. As they collapse, they heat up. Eventually, the temperature and pressure at the center of these collapsing clouds become high enough to ignite nuclear fusion. The first stars are born. These first stars are very different from the stars we see today. They are much more massive and short-lived. They burn brightly for a few million years before exploding as supernovae. These supernovae explosions enrich the surrounding gas with heavier elements, paving the way for the formation of more diverse stars and galaxies. Section 10. From gas clouds to galaxies, the cosmic web emerges. The first stars are not isolated objects. They form in clusters within larger clouds of gas and dust. Gravity draws these clusters together, leading to the formation of the first galaxies. These early galaxies are smaller and more irregular than the majestic spiral and elliptical galaxies we see today. Over billions of years, galaxies interact and merge, growing larger and more complex. Gravity sculpts the distribution of galaxies into a vast cosmic web, with clusters of galaxies connected by filaments of gas and dust. Section 11. The Expanding Universe, a Journey Without End. This chapter delves into the mysteries and wonders of our ever-expanding universe. The universe's story doesn't end with the formation of galaxies. These magnificent structures are just one chapter in the cosmic tale. The expansion that began with the Big Bang continues today, driving galaxies further apart. Distant galaxies are moving away from us, and the farther away they are, the faster they are receding. This phenomenon is a key piece of evidence for the universe's ongoing expansion. This expansion is not caused by galaxies moving through space. Instead, it's the fabric of space itself that is stretching, creating more space between galaxies. Instead, it's the fabric of space itself that is stretching. This concept is fundamental to our understanding of cosmology. The implications of this expansion are profound. It challenges our perceptions of the universe and our place within it. It suggests that the universe may have no edge and no center. This infinite nature is both awe-inspiring and humbling. As the universe expands, it also cools. This cooling process has been ongoing since the Big Bang. The cosmic microwave background radiation, the afterglow of the Big Bang, provides evidence for this cooling. It is a snapshot of the universe in its infancy. As we look back in time to the early universe, we see a universe that is hotter and denser than the universe we observe today. This glimpse into the past helps us understand the evolution of the cosmos. The future of the universe is uncertain. Will it continue to expand indefinitely, or will other forces come into play? Will the expansion continue forever? This is one of the great questions of modern astronomy. Will the universe eventually collapse in on itself in a big crunch? This hypothetical scenario is a topic of much debate and research. These are questions that astronomers are still trying to answer. The quest to understand the universe is a journey without end, filled with endless possibilities and discoveries.